Hello and welcome. So with this question, we're going to be doing an application of the Solow model, and this is going to be the full model, with technology growth, labor augmenting technology, as well as population. And the question that we have is, what is the effect of an increase in the population growth rate? I guess I should reword this. So the plan of attack is going to be to analyze things through the Solow diagram. And then we'll think about how things are going to look through time. So we use transition dynamics, look at transition dynamics given this higher population growth rate. Also keep in mind that this particular video is one of many covering the Solow growth model, so have a look at the video description if you want more help. So turning to the Solow diagram, this guy. So what is the effect of a change in population growth? Using the notation that I've been carrying through, this N is our population growth rate. So it's how our labor supply changes through time. So an increase in the population growth makes this number bigger, right? Obviously. And using the Solow diagram, that'll increase the steepness of this blue line. So what is the blue line? The blue line is what we call the break-even investment line. So it's kind of given some value of capital per worker or capital per effective worker down here. This blue line tells you how much capital you need to add this period in order to keep that capital per effective worker stock constant, right? So things can reduce the capital per effective worker stock, right? So depreciation obviously destroys capital. The growth rate of technology, if we're trying to keep capital per effective worker higher, but technology is bigger, we need to produce some additional capital to give those new effective workers. And then similarly, with population growth, if new people are being added to the economy, they're being put into the production function, they need to have that new population, that new labor, the new L, they need to be given some additional labor. They need to be given some additional capital as well. So in order to keep capital per worker constant, the capital per worker stock needs to increase with population growth, right? Because there's new workers entering the workforce, and those workers need capital as well. So that's why we added that N in there, and that's what this blue line means. It's the amount of capital that needs to be produced each period to keep the capital per effective worker stock constant. Cool, so that shifts up this line. We're going to assume as a starting point that we were at the steady state level of capital. So we were at this K star. So what happens if the growth rate of population shifts up? Well, obviously this blue line shifts up, and that's going to push the intersection down the investment line, somewhere down here. To see that visually, let's look at that Wolfram Alpha demonstration. So this is free from Wolfram Alpha if you want to check it out. What if we increase the population growth rate? So let's say we were here. If we increase population growth, we could see the slope of that break-even investment line, this one that's yellow. The slope of that break-even investment line is going up, which is pushing the intersection down and producing a new lower level of steady state capital per effective worker, capital per worker. So we were there, and with higher population growth, we now have a new steady state level. Cool, so we have a new steady state level, but what does it look like? What do the variables of interest look like through time? So we're going to turn to the time series stuff now. And how I'm going to do that is, I built this little Excel spreadsheet, which is pretty straightforward. We have, all of the variables of interest that we care about. I arbitrarily started off with certain values of capital as well as, savings rates and stuff. And then what we're going to do is we're going to change the population growth. I'm kind of making an absurdly big change in population growth just so you can see it clearly in the graphs. And we'll see how things change. So how do things change? Well, let's start off with capital per effective worker and capital per worker. It's actually going to be the same story for both with this population growth. Before we, remember we were at that initial level, that initial steady state level of capital per effective worker, and we were at that initial level of capital per worker right here. That's the initial steady state level. And then if we decrease the growth rate of population, that shifted up that break-even investment line, resulting in a new steady state level of capital per effective worker. So it pushed us down to this new lower level down here, right? However, the shift, even though the steady state level changed instantaneously, it changed the moment the population growth rate increased, Capital is defined by that capital accumulation equation, and capital doesn't change instantaneously. So it evolves through time. If you want to increase capital, you need to invest and add to the capital stock. If you want, for some reason, the capital stock to decrease, you need to allow depreciation and the other forces to decrease capital stock. So we're curious about what this transition dynamic is, right? Well, if the current capital stock, remember we're starting way up here, is higher than the steady state capital stock, what happens? Well, let's look at the diagram. So if this is the steady state down here, this K star, and for some reason we're at a higher capital stock, capital per effective worker stock up here, which is the situation we're looking at, we can see that this blue line is above the investment line. So the break-even investment line is above the current investment line. So what that means is, remember, that line's the amount of capital that needs to be produced each period just to keep things constant. And then this red line is investment line, which is how much investment is being converted into capital. So this blue line is above the red line if the break-even amount of capital required is above the amount that's actually being invested and added. We know that capital stock is going to decrease, and it's going to be decreased by the difference here, because this is how much is actually added. This is how much is needed to be added to keep things constant. So the difference is how much capital is going to decrease. So initially, if we're way, let's suppose we're at a capital level way over here, then there's a big difference between that break-even line and the investment line, and then there's going to be a big reduction in the capital per effective worker. So this difference here is how much capital per effective worker is going to decrease. So one period goes by and we decrease capital to a new lower level. So now we're at this level over here, and the break-even line is still above the investment line, but it's not as above as it was before. So things are going to, capital per effective worker stock is going to decrease, but not as big of a decrease as the initial one. So we decrease it a little bit, and once again we see that the break-even investment line is above the investment line. However, it's not as big as it was before. So you can see how things are converging towards the steady state, and the initial moves were very large, but as we get closer to the steady states, the moves are smaller and smaller and smaller and smaller. And that's exactly what we see here. So we see the initial move, given the change in the growth rate of the population, is very big, but it gets slower and slower and slower as it approaches the new steady state level. So that's dealing with capital per effective worker. So let's look at capital per worker. We're looking at log values because when this right here is with population growth and technology growth. And with technology growth, things are growing exponentially. So you got to convert them into logs so that you have a nice straight line. So this line right here is the growth rate of technology. And yeah, I made a nice little chart that summarized everything for you. So this chart kind of summarizes for each key variable what shifts growth rates and what shifts levels. So capital per effective worker, we just walk through. The growth rate is 0. It's at a steady state in the version of the model we're looking at, and we've changed population growth. So population growth goes up, this level shifts down. So now we're looking at capital per worker in the time series. Capital per worker, the growth rate is defined by the growth rate of technology, that's G, so that's unchanged. So capital per worker is going to continue to grow at the same rate. However, we are going to be shifted to a new lower level, and that new lower level is going to be concurrent with the transition for capital effective worker to the new lower steady state. So that's what we see. We see that we were at this initial kind of steady state growth path where capital per effective worker is at a steady state, and then this is just growing at the growth rate of technology. And so we increase the population growth rate and we get shifted down to this new lower level. So initially, capital per worker is being shifted down, growth is actually being reduced. So the growth rate's negative for a while, but eventually it catches back up to the growth rate of technology as it reaches that new path. Output per worker is just a function of capital per worker, so you get essentially the same kind of process going on there. And then in this case, consumption and investment per worker follow the same process. So let's look at aggregate levels. So what defines aggregate levels of capital and output? Well, we see that the level effects are savings and depreciation, but then the growth rate of capital and the growth rate of aggregate output are defined by the growth rate of technology, G, and the growth rate of population, N. So unlike the level effects we saw with the per worker stuff and the per effective worker variables, when we're thinking about aggregate amounts of capital and output, the thing that we're changing now is the growth rate. So because population growth is higher, this N's larger, that means capital and output, as well as investment and consumption, are going to be growing at a higher rate now. So looking at it in a time series, this is where the growth rate of capital and this is the growth rate of aggregate output. That was just, once again, that's G plus N, so that's the growth rate of technology plus the growth rate of population. And so at this dotted line, that's the moment the population growth shifts upwards. And so we see that these two aggregate levels are, these aggregate values, variables, are growing now at a higher rate. So simple as that. One thing that's always confusing to me is we increase the population growth, and yet the steady state level of capital per worker and output per worker reduced, but aggregate output increased. Like that might be, for some people, kind of confusing, right? So we see this thing increasing. This is aggregate capital and aggregate output. That's kind of a proxy for how the economy is doing overall, right? So we're at a faster rate with higher population. But when we look at per capita levels, whoa, things are worse off, right? So it's kind of confusing. And I like to make the comparison to, let's say, Japan and the U.S., right? So Japan and the U.S. has a noticeably higher population growth rate than Japan. So that's the first off. In fact, I think Japan maybe technically has a negative growth rate in its population. And so you sometimes compare GDP, aggregate GDP, to Japan and the U.S. And it's kind of, from my mind, I see these articles and they kind of talk about stagnant growth in Japan. But you might actually expect that if the population growth is being reduced, right? So the U.S. has a higher population growth, so you expect it to have this higher path for aggregate output. But the question is, well, how are things doing on a per capita level? And so, there's kind of a complicated story that I'll gloss over. But if you look at per capita levels of GDP growth for Japan and compare that to the U.S., it's actually doing pretty well. It's not doing that bad in comparison to the U.S. And that would make sense, right? Because with a higher population growth, as new people are added to the workforce, those new people need to be given capital, right? So you need to be producing additional capital and additional resources for all those new people being added to the workforce in order to make them contribute as much as the existing workforce. So output per worker here, with a higher population growth, gets shifted down to this lower level. So the growth rate doesn't change, but it gets shifted down to this lower level with higher population growth to take into account the fact that investment needs to increase so that those new workers being added to the workforce are given a certain amount of capital so that they can contribute in the same way that the previous workers have. Hopefully that was clear. It's basically, the thing that we should be concerned with is output per worker, because that's like, how are people doing in general on average? And you might be confused with this. This might make it appear that the economy overall is doing much better with higher population growth. But in one respect, we should be concerned with per capita levels. What's the average or the median worker doing? And we see with higher population growth, things are a little bit worse off because all of those new workers, those new people being added to the workforce, they need to have resources. The investment needs to be higher to take into account them. However, the growth rate, right, of these per capita levels, that's just defined by technology. So that's unchanged here. Okay. Yep. Hopefully that was helpful. My focus was on the nitty-gritty details of the model rather than too much of the intuition. So hopefully your professor or TA will help you with that. Thanks and have a good day. If you found this helpful, be sure to give it a like, and thanks.